Hello everyone and welcome to our presentation. Today we're excited to introduce you to the Vernacular voice chatbot. My name is Srishti and alongside Lucky, we will be guiding you through this session. We also want to acknowledge our mentors, Sarvesh, Pushkar and Shashi, whose guidance has been invaluable. Over the next few minutes, we'll cover what this chatbot is all about, how it works, and the impact it can have. So let's dive in and explore this innovative project together. All right, let's take a quick look at our agenda for today. We'll start by discussing the core problem we're addressing, then move on to our approach with speech technology, specifically focusing on large language models and text-to-speech systems. From there, we'll explore future improvements to make our vernacular voice chatbot even more effective. And of course, we'll look ahead to what 2025 might hold for this exciting project. This agenda will guide us through understanding how all these pieces come together to create a more natural and accessible voice interaction experience. Let's talk about the problem first. Many Indian customers find it challenging to use banking apps that are primarily in English. This language barrier really limits financial inclusion because it makes it harder for a large segment of the population to access and manage their finances easily. Now, here's where the solution comes in. Imagine an AI voice bot that can understand and respond in the user's own language, whether that's Hindi, Tamil, Marathi, or any regional language. This voice bot acts like a customer support agent, making banking services more accessible and user-friendly. By bridging the language gap, we can help more people participate in the financial system comfortably, ultimately driving greater inclusion across India.
I can help you with that. Can you please provide your account number?
Yeah, hold on.
Let's take a closer look at the model we're using for speech-to-text and WebRTC integration. We're leveraging Google Cloud SDT, which provides robust streaming audio capabilities. The idea here is to stream audio in real time, allowing for more dynamic and immediate transcription. To facilitate this, we're using WebRTC to stream audio directly from the user to the server and back, enabling low-latency communication. On the user interface side, we're utilizing Streamlit and Streamlit WebRTC. These tools help us create an intuitive and responsive interface, making it easier for users to interact with the system seamlessly. For voice activity detection, or VAD, we're employing Google's VAD model. This helps us accurately identify when someone is speaking, so the system only transcribes relevant audio segments, improving efficiency and accuracy. Now, regarding our benchmarking results, we've achieved about a 15% word error rate when testing on 10 hours of Hindi audio data collected from YouTube. This gives us a solid baseline for the model's performance, especially considering the complexity of real-world audio in different environments. Overall, this slide highlights how combining these technologies, Google Cloud SDT, WebRTC, and VAD, allows us to build an effective real-time speech recognition system, which is central to our project's mission of making speech-to-text more accessible and accurate. Let's talk about some of the challenges we face in speech-to-text systems. One of the main issues is dealing with different uses and, consequently, different needs. For example, the way speech is represented can vary widely, whether it's the layout, sample rate, audio format, or frame size. Each of these factors requires careful consideration to ensure accurate transcription. Another challenge is adjusting voice activity detection, or VAD, parameters. Getting VAD right is crucial because it helps the system distinguish between speech and silence, which impacts overall accuracy. Model selection is also a key point. We need models that balance performance with latency. For instance, we experimented with fine-tuned faster whisper models specifically for Hindi to reduce delay. But ultimately, we settled on using Google Cloud's SDT model because of its reliability and scalability. Looking ahead to 2025, our goal is to develop a vernacular voice chatbot that can handle diverse languages and dialects effectively. All of these efforts are part of our broader vision to make speech recognition more accessible and seamless for users everywhere. Let's take a closer look at how we're enhancing the retrieval augmented generation, or RAG, process with large language models. First, we store relevant information in a vector database, which allows us to efficiently retrieve data based on semantic similarity rather than just keywords. This is a key step in making the system more intelligent and context-aware. Next, we use a technique called agentic chunking. Instead of simply breaking text at punctuation or fixed lengths, we create chunks based on the meaning of the content. This ensures that each chunk makes sense on its own and preserves the context, which improves the overall retrieval and response quality. Our intermediate chatbot, built entirely in LangGraph, orchestrates this process. It manages the flow and ensures that each step, chunking, retrieval, and response generation, is seamlessly connected. For the large language model itself, we're using Gemini 2.5 Flash. One interesting feature here is that we perform multiple LLM calls to verify if a user's query is clear and sufficient before generating the final response. This helps us avoid misunderstandings. If the query isn't complete or needs clarification, the model can even ask questions back to the user, making the interaction more conversational and effective. Now, let's talk about the tools involved. We include a document search capability that leverages MongoDB's geospatial query features. This allows us to find nearby locations based on user input, which is particularly useful for applications like the Vernacular voice chatbot, especially as we look towards 2025. All these components come together to create a smarter, more responsive conversational system that can understand, retrieve, and interact more naturally. Let's talk about some of the key challenges we face with large language models. One major point of comparison is between chatbots and voice bots. While both are powerful, they come with their own set of issues. For instance, verbosity is a common challenge. We often need to shorten the output to make conversations more natural and engaging, so users don't get overwhelmed or bored. Another challenge is looping. Sometimes, the system ends up asking a series of questions repeatedly to clarify or form a complete query, which can be frustrating for users. Then there's the matter of data, both quantity and quality. High-quality data is crucial for training effective models. Unfortunately, we often lack sufficient quality customer service data, especially for retrieval-augmented generation mechanisms, which are designed to improve responses by referencing external information. To address some of these issues, we might generate random or proxy user data for testing purposes, especially when real data is scarce. Looking ahead to 2025, the focus is on developing vernacular voice chatbots, more natural, conversational, and aligned with everyday speech patterns. Overcoming these challenges is essential for creating voice AI that truly feels human and intuitive, fitting seamlessly into our overall goal of enhancing user experience. Let's talk about the TTS model we're using. We're leveraging Google's GTTS engine through a real-time wrapper called Real-Time TTS. This setup allows us to generate speech on the fly, which is essential for our interactive voice chatbot. However, there are some challenges. One major issue is integrating TTS smoothly with WebRTC, especially when it comes to managing interruptions during speech playback. We've encountered threading and blocking problems, mainly due to limited documentation around the Streamlit WebRTC package we're using. Automatic interruption mechanisms, which are supposed to stop speech when needed, ended up creating processing issues. So our current workaround is to bypass Streamlit WebRTC for TTS altogether. Instead, we handle real-time streaming for speech-to-text and large language model components, then generate TTS separately. The TTS output is saved as a WAV file, which we then play through Streamlit. This setup also gives users the ability to manually pause the speech output if they want, replacing automatic interruption. It's a more reliable approach given the current technical constraints. Overall, this approach helps us keep the interaction smooth while working around the limitations of our tools, bringing us closer to a natural, vernacular voice chat experience. So, for this part of the project, we created API endpoints specifically for the language model component and deployed them to the cloud. The main reason was to facilitate testing and integration in a real-world environment. We chose Google Cloud Run for this purpose because it offers a scalable and serverless platform, making it easier to manage and deploy these APIs without worrying about infrastructure. Right now, we've stored the vectors within the same Docker container that we upload to the cloud. While this works for initial testing, it's not ideal for scalability or performance in the long run. So, our next step is to outsource this storage to a dedicated cloud-based vector database, which will improve retrieval times and overall system efficiency. You can test these APIs either through Postman or by using this web-based tool at Yaman, GitHub, io/test chatbot. This makes it straightforward to verify that everything is working as expected and to troubleshoot if needed. Overall, deploying these components to the cloud is a crucial step in making our chatbot more robust and ready for real-world use. It aligns with our goal of creating a scalable, efficient, and easily testable system. Let's explore some exciting future improvements we're working on. Currently, our system only supports Hindi, but one of our main goals is to expand language support to make it more accessible worldwide. We're also aiming to develop truly real-time text-to-speech, which will make the interaction feel even more natural and seamless. Additionally, we want to enable playing output speech via WebRTC, allowing for smoother and more integrated communication experiences. Another key area is dynamic prompting. Moving away from static prompts and a linear workflow means the system will become more flexible and adaptable, responding more intelligently to user inputs. Lastly, automatic interruption is a big focus. This means the system will be able to detect when the user starts speaking and interrupt or adapt accordingly. This will lower latency and improve accuracy, making the entire interaction feel more fluid and responsive. These improvements are all about making our system more natural, efficient, and user-friendly as we continue to develop and refine it. Thank you so much for your attention. I really appreciate you taking the time to go through this presentation with me. I hope the insights we've shared today have been valuable and thought-provoking. Remember, the key points we've discussed, whether it's the importance of innovation, collaboration, or continuous improvement, are all essential to achieving success in our field. I encourage you to take these ideas and apply them in your own work. Again, thank you for being such an engaged audience. I look forward to seeing how you all implement these concepts moving forward.